this column is the one you mainly want to look at. The true value was -1, right? The mean of our samples is minus 1.01, so very good parameter recovery. We got back the truth. This one was 0, this one was 1, that was 1, that was 0.2. So this has worked. We can know this has worked well. When you're using this on data though, there are some important things here, like there's the 95% credible interval on the estimate. It lies somewhere between minus 1.02 and minus 0.994. So it contains the true value. And it's very tight. Often you will see in a Bayesian paper, what they will do is they will plot those posterior parameter distributions to summarize their influence. They'll give that histogram that we drew earlier on. Maybe I'll show you with some. You could get them yourself because Coda.
我跟大家解释一下，就是说你现在做了这个 samples 之后，你会得到一个 posterior distribution。那他刚刚就是看，他刚刚有用一些方法去看说这个 posterior distribution 是不是够好的。然后再来就是说，我们有了这个 posterior distribution 之后呢，你就可以去建构它的95%的信赖区间。那现在要做的事情就是怎么把那个95%信赖区间把它建构出来。所以你可以记得，我们刚刚有设定它的，我们认为它的 true value 就是它的真实参数值，我们把它设在1。然后你可以看到它的信赖区间大概是介于就是在那个附近嘛，所以它有包含了那个真实值，所以就代表说我们的结果其实是有 simulate 出来那个有逼近原来的那个我们想要看的母群的长的样子。那个 posterior predictives 就是说，我们在用我们预测出来那个参数，我们去产生新的 data。那看这个产生新的 data， 我们再把它去看它的 fit 出来的参数值是不是很接近于原来母群的真实参数值。
Okay, thank you. So here I've drawn, I just did the plot B and C here and I turned off the trace. So now we just get the histograms. So when I say, for example, here for mean log true, its 95% credible interval is between minus 1.02 and 0.99. What I mean is that 95% of this histogram lies between about there and about there. Right? You'll often see this is how a Bayesian will summarize there. So there they are the posteriors. That is your state of knowledge after viewing the data. It's not a single number, it's a distribution. But we can use single numbers like the mean or a pair of numbers like the credible interval in order to summarize our knowledge. Okay?
所以你们可以看到103行那个 post predicted， 就是说它有画2条线，应该说有4条线，但是有实线跟虚线。所以你可以看到它那个不同的线，所以就是有实线跟虚线。实线就是观察到的资料，然后虚线就是它实际那个 based on 那个它产生出来的那个估计出来参数值，然后重新去画它的图，其实它很接近，就代表我们预测的还不错。然后这边是在画的是 posterior distribution， 所以就是它把那个参数值的那个事后几率的分布图把它画出来，然后怎么去建构它的那个信赖区间的过程。
Another useful.
这个是下面。
Another useful plot is to look at the correlations amongst the parameters. You can do with this with the pairs function. This is big, this can take a long time to run sometimes, and to draw. Remember those pictures I showed you in my overheads? This is produced by pairs. You can see here that the correlations amongst the parameters are not very high in LFR. This is the biggest one between SD log false and T naught. it's a correlation of about there's 0.69, there's a big one, between T naught and ST log true. That's a 0.7. When you draw this, the LBA and the DDM, you'll get 0.9. You'll get strong streaks across it. So this is what makes life difficult. Now, it's just the truth. It's the way the model works. So, but it's a useful thing to look at and think about. Gelman is one of the big guys in Bayesian statistics, and one way that he likes to do to understand whether a model fits well is to calculate something that's like a Bayesian p-value. The idea is that you might have some particular statistic of the data that you're interested in. It's not a sufficient statistic, it's not everything. So the PDF and the CDF, those graphs that we just showed you, they're sufficient. They contain everything there is to know. But you may want to focus on some particular thing. Here, what I chose to do was to focus on the interquartile range. That is the distance between, here I wrote a little function to calculate it, between the 25th percentile and the 75th percentile of the RTs. Okay? So there I've calculated it. I wrote a function to do that. This is a slightly advanced bit, I should say. Here I'm encapsulating this inner function to get the IQR, the interquartile range. So I define a function, and when I run it on the data, it tells me that the interquartile range is about 0.1. Here it was 0.09, right? Roughly the same. So this might be my target thing. I want to say my data's interquartile range is 0.1. Now I'm going to simulate out of my model, and I'm going to calculate the interquartile range for my model again and again and again. And I'll get a distribution of interquartile ranges. And then I'll draw a graph. There it is happening. I'll draw a graph and I'll say, is what I observed in the middle of this distribution? Because if I've got the truth, it should be sitting in the middle of the distribution. In other words, the Bayesian uncertainty should spread around the true value. However, if the true value is outside of the posterior predictive distribution, so there it is. So what this graph is showing you is this histogram is me repeatedly sampling again and again and again and again and again and calculating interquartile ranges. There's the true value from the data, and notice that the true value sits right in the middle of my simulated distribution. And in fact, I can calculate a p-value. It's not an evil p-value like for ground statistics, it's a nice one. And if it's around the middle, 0.5, things are good. If it's either very small or very large, then things are bad. Now look, we're at the end of this lesson, and I think everyone's brain is probably totally full. So I don't know where, one thing you could do is everyone just spends a while running through the LBA lesson. The only thing to say is I have about half an hour more material on model selection. What should we do? So I agree. Everyone is like, oh. Yeah. Okay, we get coffee, we relax, and then we start. Thank you very much, Jim. That's very good explanation. See, this is very practical. Yeah, absolutely.